Load break switches. So the load break switches are a special type of disconnect switch. So that has been equipped to provide the breaking and making of a specified current. So there is a device called arcing horns attached to the disconnector or the isolator. So they are it allows the isolator to interrupt very small amount of charging or magnetizing current. Okay, so you can see here the arcing horns on a vertical breaker switch. Okay, so the capability of the arcing horn to perform a current interruption is a function of arcing horn material. So the ability to interrupt the currents depending on the material of the arcing horn. So you can see it's in here. So the typically it's made out of copper or a stainless steel. Okay, so the standard arcing horns can be used on any kV rated switches or the isolators. Okay, so the standard arcing horns, they do not have load breaking capability, so keep this in mind. So just connecting the arcing horn to the isolator won't make that isolator capable of uh, disconnecting the load current. So it's not for the that purpose. Okay, so the breaking capacity and so these arcing horns, they do not have load breaking capacity. Okay, so they should not be used to perform a load breaking function. Okay, so that you need to keep in mind. And there is a special type of arcing horns called the high speed arcing horn, or the what we call the whip horns. So these are the equipment added to disconnect switches to allow them to interrupt a small amount of charging or magnetizing current. Okay, so the quick break whip type arcing horns are, they are suitable for use on disconnect switch rated 161 kV and below. So these quick speed arcing horns are specifically used for only for use in the 161 kV or below voltages. Okay, so and this whip type arcing horns, they do not have load breaking capacity, as we discussed earlier for the general arcing horns, and they should not be used to perform a load breaking functions. Okay, so just connecting the arcing horn does not say that it is capable of breaking the load current, but it is capable of handling a little more current than the typical isolator. These currents could be a magnetizing current, so uh, or things like that, and so they can handle little more current than the typical isolators. Okay, okay, so okay, let's talk about the load break switches. So then so just an isolator with arcing horn will not be act as a load breaking switch. So there should be a special arrangement to make the switch the load breaking switch. So this type of switches we also call the interrupter. So here you can see the load breaking switch with a SF6 interrupter in this figure. Okay, so if you need to interrupt the loop current, load current, or large amount of line charging current, okay, then disconnect switch can be outfitted with an interrupter. So you have an interrupter as shown in here. So this interrupter can be can use either sulfur hexafluoride or SF6 gas or vacuum as an interrupting medium. Okay, so okay, so this is then capable of performing interruption for the high currents like load current or large amount of line charging current. Okay, so most commonly the type of disconnect switch outfitted is a vertical break switch. So typically the vertical break switches are outfitted with this what you call the interrupters. Okay, So single side brake switch are sometimes used. Okay, so mostly they use the single side braking switches equipped with the SF6 or the vacuum interrupters, interrupt medium, in order to facilitate the high current braking. Okay, so at 30 kV and below, center brake switches can also be used, or center brake V switches can also be used, but in a low voltages like 30 kV or below. Okay, okay, so let's see different types of load braking switches. So you have a load braking switches with a SF6 gas. Okay, so load line or loop interrupters. So they are single gap type for all kV rating. So you have only one uh, gap type for all kV, and that it will look something like that. So inside this arrangement you have this interrupter with a SF6 gas. Okay, so the later we will see how it's typically happen. Okay, and then the vacuum load line or loop interrupters. So vacuum interrupters, so they come with a different arrangement for different voltages. Okay, so they are multiple gap type for system voltage above 30 kV. So if the system voltage is greater than 30 kV, you can use multiple gap type systems. Okay, so here you can see a load brake switch with multi-bottle vacuum interrupt. So you can see there are number of bottles, 1 2 3, uh, the vacuum bottles which handle the interrupts. Okay, so at 34.5 and 46 kV, typically 2 vacuum bottles per phase is required, and at 69 kV 3 of them are required. At 115, 5 of them are required, and you can see that as the voltage rises, the number of bottles needed to quench the arc or the perform the interruption is increased. For 230 kV you need 8 such bottles. So that means as the voltage increases, the length of this device increases, so the size of the load brake switch will also increases. Okay, okay, and then another type of the device that you can find in a substation is called the power fuses. Okay, so the power fuses are generally accepted means of protecting small power transformers. So power fuses are basically used to protect the small power transformers which are 15 MVA and smaller. Okay, so and they can also be used to protect the capacitor banks and the potential transformers and or station service transformers. Okay, so basically protection of small power transformers and the other type of transformers, as well as the capacitor banks in the substation. Okay, so okay, so the purpose of these power fuses is to provide an interruption of a permanent fault. Okay, so if the fault happens in the system, permanent faults happen in the system, then you need to disconnect the system from the fault. So in order to do that, you can use these power fuses. Okay, so these power fuses are economical alternative to a circuit switcher or the circuit breaker. So instead of a circuit breaker, you can use the power fuses for low power devices like low power transformers and capacitor banks and so on, with the as an economical solution. Okay, so use protection is generally limited to voltages from 15 to 69 kV. So these are the voltage range typically that you can use power fuses. Okay, so if the voltage is high, then you have to go for the alternative. Okay, so the one of the alternative for the power fuses is the circuit breakers. So these are mechanical switching device capable of making, carrying and breaking current. Okay, so you can carry the current in a typical or normal operation, and you can break the current when the fault happens, and you can make the circuit while the current is flowing in the circuit. Okay. So under normal circuit condition, and also making, carrying and breaking for a specified time. Okay. So this making, carrying and breaking can be done for a normal circuit condition, and for a for abnormal conditions such as short circuit as well, and the breaking current under specific abnormal conditions such as short circuit. So you can carry the normal circuit condition, and then you can perform the breaking when the abnormal current is detected, like such as a short circuit current. Okay. So they can be classified according to the interrupting medium. So you can use either vacuum, oil or SF6 gas as an interrupting medium. Okay. So if you use the vacuum, so they are used for switchgear applications and for some outdoor breakers. So you can use the vacuum uh, circuit breakers. So they are generally used in 38 kV class and below. Okay, so if the the voltage is 38 kV or below, you can use the vacuum circuit breakers. Okay, so the oil circuit breakers, so these have been very widely used in utility industry in the past, but now they have been replaced with the other technologies such as the SF6. Okay, so SF6 can be used in the higher voltage and the higher current scenario, because it has the capability of breaking under very high voltage and very high current. Okay, so here you have a couple of videos about circuit breakers. So here I want to
This is an Alstom 132,000 volt circuit breaker. It's fairly common these days. The interrupting and insulating medium is sulfur hexafluoride gas, not oil. How it works is, up in the top section there's a copper rod which moves up and down. From there downwards there's an insulated rod, really tough fiberglass usually, because you've got to keep that away from that. That's all earth and that's live. So insulate.
shared the slides. Okay, and then next I have another video which basically
Hello friends.
Talk about
Welcome to Tech Talks Engineered channel. Today we will discuss about SF6 circuit breaker. We will see its close and open operation inside interrupter and also a practical demonstration. Breaker. This is 220 kV SF6 circuit breaker, and this is single pole of two main components. The longitudinal section of interrupter. If we look close, this is side porcelain housing. We can see two main contacts. This one is male contact which is moving, and this other one is female contact which is fixed. This is how these two contacts look like. If we look closely,
get the actual feeling, what's inside this circuit breaker. Typically what you will see is something like this. So but everything is inside, so you will see what are the things inside in this video. Okay, so the next type of devices that you can find in the substation are current and voltage transformers. Okay, so they are used to for the measurement purpose. Okay, so what they will do is they will convert the higher voltage and currents typically available in the bus bars in the substation. They will convert into the more manageable quantities to facilitate the measurement, protection and control. Okay, so let's take a look at the current transformer. Okay, the current transformer is used to transform a primary current quantity in terms of magnitude as well as the phase to a secondary value. Okay, such as a nominal condition, such that in the nominal condition the secondary value is substantially proportional to the primary value. Okay, so you have a primary current which is basically the current that flowing in the bus bars in the substation and these the lines, and then what we will do is you will convert these the currents into a more readable currents in the in order to do the measurements as well as in order to activate the protection and the control. Okay, so we can classify the protection CTs. Okay, so the unlike the measuring CTs, the protection CTs may be required to operate at a many times full load current. So these protection current transformers should be able to measure the fault currents which are many times the full load current. Okay, so linearity under this condition is not of great importance. So you don't mind whether the relation is linear or not, but what's matter is you should be able to withstand this current and should be able to take the measurements. Okay, so the essential point is that saturation must be high enough to drive the magnetizing current and the secondary current under the fault condition. Okay, okay, so we will take a look at some terms related to these current transformers and potential transformers, what we call the CTs and PTs. Okay, so the first term is rated primary or secondary current. Okay, so this is for the current transformers. Okay, so this is the primary or secondary current upon which the performance of the transformer is based. Okay, so that is the current in the bus bar or the lines. Uh, so the are the rated primary or secondary current. Okay, and the secondary current is the current at the measurement site. Okay, so the rated transformation ratio, so ratio of rated primary current to rated secondary current is known as the rated transformation ratio. So it's a the typical thing that you talk about the transformers. Okay, so this may not be necessarily exactly equal to the turns ratio. Okay, so because we talked about the PTs and there is some sort of a saturation happens, the relationship is not no longer a linear for a high currents. So because of that, the ratio may not be the same as the turns ratio. Okay, and the magnetizing current depends upon the magnitude of the primary voltage. Okay, which in turn depends upon the magnitude and power factor of the burden. Burden is the load. Okay, so and there's another term called the composite error. Okay, so the composite error is is defined as the under the steady state conditions, the RMS value of the difference between the instantaneous value of the primary current and the actual secondary current multiplied by the rated transformation ratio. Okay, so that's how the composite error is defined. Okay, and the rated output at rated secondary current is defined as the value marked on the rating plate of the apparent power in VA that the transformer is intended to supply to the secondary circuit at the rated secondary current. So this rated output at rated secondary current is marked at the transformer plate. So this is the apparent power. So that the transformer is intended to supply to the secondary circuit at the rated secondary current. Okay, and you have then the rated accuracy limit factor. Okay, so the primary current up to which the CT is required to maintain its specified accuracy with rated secondary burden connected is defined as the rated accuracy limit factor. Okay, so this is expressed as a multiple of rated primary current. Okay, so it is a integer multiple of rated primary current. Okay, So ideally, the rated accuracy limit factor current should not be less than the maximum fault current of the circuit. Okay. Okay, so let's take a look at the typical marking on a protection CT. Okay, so it would looks like something like that. So your protection CT would be marked something like this: 15 VA class 5P 10. Okay, so where this 15 VA is the VA output at rated secondary current. Okay, so VA output at the rated secondary current is the first part of this marking. Okay, and the class 5P indicates that this is a protection CT. So this P indicate that it is a protection CT with a composite error of less than 5% at rated accuracy limit primary current. Okay, so this 5 represent that it's a class 5P. So the class 5P means it's a protection CT with the composite error less than 5%, okay, at rated accuracy limit. Okay, and 10 is the rated accuracy limit factor, okay, RALF for the CT. So this 10 is the rated accuracy limit factor. Okay. Okay, so this curve shows the typical magnetizing characteristic of a transformer, and we have a knee point at this point. Okay, so for protective purposes, current transformer specifications may be defined in terms of the knee point. Okay, so for the protective purposes, so this the transformer specification may be defined at the knee point. Okay, this is the voltage applied to the secondary terminal of the CT with all other windings being open circuited. Okay, so with all other windings being open circuited, so you apply the voltage to the secondary terminal of the CT. Okay, so then you increase the voltage by 10%. Okay, so causes the existing current to be increases by 50%. So you can see that in here, so from the knee point you increase the voltage by 10%, increases the current by 50%. So after this point there is no linear relation for the transformer. Okay. Okay, and according to the BS 3938 standards, okay, so the standard catered for the specification of class X CTs in terms of rated primary current, turns ratio, rated knee point EMF, maximum exciting current at a standard percentage of a rated knee point EMF, maximum resistance of the secondary winding, and so on. So the standard define the values. Okay. Okay. So let's take a look at the metering CTs or the measurement CTs. So for non-protection purpose, that means basically for measuring purpose. Uh, So these metering CTs need to perform very accurately, but only over the normal range of the load. Okay, so the measurement should be very accurate, but they are limited only to normal range of the load. Okay, so up for an example, say up to 120% of full rated uh, full load current. Okay, so that's in that range if the measurement should be very accurate. Okay, so the metering CTs, they are specified in terms of ratio. Okay, rated VA secondary burden and the accuracy class. Okay, and the accuracy class is recognized by this IEC 185. Okay, so they are 0 0.1, 0 0.2, 0 0.5 and 1. Okay. For each of these classes, the ratio and the phase angle error must be within the specified limit. Okay, so at 5, 20, 100 and 120 of the rated current. Okay. A class 0.2 metering CT means that at 100 to 120% of the rated current, the percentage ratio error will be plus or minus 0.2. So that's what is defined by 0.2. Okay, that is for a class 0.2 CT with a rated secondary current of 5 ampere. The actual secondary current would be 5 ampere plus or minus 0.01 ampere. Okay, that means okay, so that's how this the class is defined. Okay, okay. So this shows the typical marking of the metering CT. So you have 15 VA class 0.2 120%. So the VA output at the rated secondary current is 15 VA, as you have seen it in the protective transformers. Okay, protective CTs. Then the percentage error is plus or minus 0.2%. Okay, at rated current. Okay, plus or minus 0.2% at the rated current, and the extended current rating is 120% of the rated secondary current. So it can measure up to 120% of the rated secondary current with a good accuracy. Okay. Okay, so that's about the current transformers. Okay, so the next we are going to talk about the voltage transformers. Okay, so IC 186 they talk about both the electromagnetic and capacitor type voltage transformers. Okay, so for protection purposes, voltage transformers are required to maintain specified accuracy limits down to 2% of rated voltage. Okay, so for the protection purpose, the VT, so what we call the PT, sometimes the potential transformers are required to maintain this accurate limit down to 2% of the rated voltage. Okay, so the class 3P may have 3% voltage error at 5% rated voltage. Okay, and 6% voltage error at 2% rated voltage. And the class 6P is defined such a way that it may have 6% voltage error at 5% rated voltage and 12% voltage error at 2% rated voltage. Okay. Okay. So So these electromagnetic voltage transformers, so they are functionally similar to the power transformers. Okay, but with rated output in VA rather than the kVA or MVA. So these are the rated power output is small compared to the power transformers. Okay, so this type of voltage transformers are used up to the system rated voltage of 36 kV. Okay, so above these voltage levels, the capacitor voltage transformers become very cost effective. Okay, and they are used more frequently compared to the electromagnetic voltage transformers. Okay, and these electromagnetic voltage transformers, they normally operate at low flux densities than power transformers. Okay, so the power transformers are operated at high power as well as high flux density, but electromagnetic measurement transformers, they operate in the low flux density. Okay, so it is usual to provide fuse protection on the HV side of the electromagnetic VTs up to 36 kV. Okay, so we talked about the protection of these CTs and PTs when we discussed about the disconnectors, circuit breakers, and fuses. Okay, so in addition, the fuses or MCBs are used on the secondary side. So in the secondary side, you use the fuses or MCBs because the secondary side currents and the voltages are lower compared to the primary side voltage. Okay. Uh, okay. And if the voltage is higher than what we call the 36 kV, it's cost effective to use the capacitor type voltage transformer. So they are used in series. They use the series string of capacitors to provide the voltage divider network. So as shown in here, so instead of having a magnetic or electromagnetic coupling, now you have a voltage divider arrangement built based on the capacitors. Okay, so these are the most common form of voltage transformers at rated voltage of 72 kV and higher. Okay, so and between 39 and 36 and 72 kV you may find the mix of those, but for very high voltages these are the mostly used voltage transformers. Okay, and then you use the small conventional voltage transformer to isolate the burden is the load from uh, the capacitor chain. So you have a capacitor chain here in series, basically building the what we call the capacitor or the potential divider, and then for the isolation purpose you use a small conventional voltage transformer. Okay, so nothing to do with the measurements. Okay, okay, so those are the typical equipments that you found in the substation, the main equipment, then depending on the modern technology and the technologies used in the substation, you have other type of measurements devices and the control equipments like SCADA and so on. Okay, uh, so but we discussed the very the main components that we used in a substation. Okay, so the next we are going to talk about the substation grounding. So I will break this video at this point, and then we will talk about the substation grounding after that.